Okay, so thanks once again, everyone, for tuning in. Today we have Joan Camps from University College London, who's going to tell us about his work on superselection sectors of gravitational subregions. So, Joan, thank you very much, and take it away.
Thank you very much for the invitation. It's my first online Zoom seminar, so let's see how that goes. Some of you have seen versions of this talk before, and maybe even somebody has seen exactly the same talk, so sorry for this, but hopefully if something was not clear last time, it's going to be clearer now. This is based on a paper that appeared in October. So I'm the only author of that paper, but that paper emerged as I was having lots of discussions about related subjects with Will Donnelly, Aitor Lefkovich, and Anthony Speranza. And I did learn a lot from these discussions. So I'm indebted for them for a lot of insights, although if there's any mistakes, these are only my mistakes. Okay, so what this paper studies are gravitational subregions. So first of all, let's get some motivation for studying subregions. So in many situations in physics, it's useful to think of your system as the union of its constituents. And usually when you have a field theory, you want to think of this system as having independent degrees of freedom at different points in space. And you may want to group these points in space into subregions, and then you may want to consider your system, which is your field theory, as made of subsystems, which are the different subregions of space. This is indeed a picture that seems to make a lot of sense, at least classically, but there's some subtleties with this picture when you want to think about it in quantum mechanics. The reason is that in quantum field theory, fields are operator valued distributions, and you're never supposed to consider them at one point. You should always smear them against test functions, and that makes it very hard to infinitely precise localize them. So for example, if I'm considering a subregion like the one here, which is denoted in red, and I want to consider the points in this subregion that are very close to the edge, in quantum field theory, I don't really have degrees of freedom infinitely sharply localized on the edge of these subregions. These degrees of freedom I'm thinking about should be smeared against test functions. And those will have some tails that go out of these subregions. And well, that gives some fuzziness to this separation of degrees of freedom in quantum field theory. So this is a problem that actually can be very well understood, and it can actually be regulated in quantum field theory, and that's what we will be doing from now on. So for the time being, I'm going to take the point of view that this separation makes sense also in quantum field theory. So once you have separated your system into subregions, one question you can ask if you're doing quantum mechanics is what's the entanglement between the different parts that make your system? So by the way, interrupt me at any point with questions. I think this seminar should be 50 minutes, so there should be time for questions.
We will.
Okay. So once you have divided your system into subsystems, you can ask about entanglement, and well, you don't need an introduction to that, but I'm going to give one anyway. Entanglement is this property of quantum mechanics that tells you that there is more information in the whole of your system than there's in the parts of your system. And here you have an example of an entangled state between subsystem 1 and subsystem 2. And the amount of entanglement can be measured in different ways. And the quantity that I'm going to be discussing today is entanglement entropy, which for a state like this, it's a Shannon entropy for these weights here. So as we just discussed in quantum field theory, there's some UV problems to infinitely sharply localize degrees of freedom. And when you consider these type of quantities for subregions, for example, the one I just plotted before, you run into UV divergences because there's infinitely much entanglement across this edge, or what's the same, the problem I discussed in the previous slide. Nevertheless, this divergence, as you know, is very appealing, especially for somebody with a background in GR, because, well, all states in quantum field theory have a universal divergence in their entropy, and that divergence is very suggestive because it goes with the area. So if you introduce this UV cutoff, you will find that as you try to eliminate your cutoff, your entropy diverges, but the leading divergence is with the area. So epsilon here is my cutoff. This, of course, is very reminiscent to black hole entropy, and it suggests that perhaps we can understand black hole entropy entirely in terms of entanglement entropy in quantum field theory. This has been an old dream of quantum gravity. We're not there yet, but I think it's fair to say that this connection has been understood much better in the recent years. So if we were to understand completely black hole entropy from entanglement in quantum field theory, that somehow would also require understanding how gravity itself emerges just from quantum field theory ingredients. And so we would aim for like a whole non-perturbative understanding of the emergence of gravity just from quantum field theory. So a non-perturbative understanding in Newton's constant of black hole entropy. So a bit more modestly, you can imagine that we already have some geometry that has emerged by this process or by whatever other process, and still entanglement entropy plays a role when you're trying to understand gravitational entropy. So in particular, if you're considering black hole entropy, entanglement entropy plays a role as the quantum corrections to the black hole entropy. So as you know, the entropy of black holes is given by the area in Planck units. So here we're assuming that there's already some gravity and some Newton's constants. So we have already a notion of entropy at the classical level given by the area. But then entanglement entropy still plays a role when we're considering quantum corrections to this gravitational entropy. And it's telling us about the quantum corrections. Now, this is in the context of black hole physics, and then more generally in ADS-CFT, a formula like this one has been playing a crucial role in the understanding of the emergence of a gravitating ADS geometry from quantum field theory ingredients. So in the next two slides, I'm gonna go through these last 2 points with a little bit more detail, and I'll try to explain, give some more meat to this connection between entanglement entropy and gravitational entropy in these two contexts of black holes in ADS-CFT. So just in the context of black holes, the fact that quantum corrections to black hole entropy are important is very obvious if you consider an evaporating black hole. So remember that by Hawking evaporation, black holes shrink. And that seems to contradict the second law of black hole thermodynamics, because the area of black holes goes down as they shrink through Hawking evaporation. And of course, the entropy of the universe should increase with any process. So a solution to this apparent paradox is to consider also the entropy of the quantum fields outside this black hole, and to add it to the gravitational entropy of the black hole to have the entropy of the universe. So if you consider the formula here, which is the sum of the geometric entropy and the entropy of the quantum fields outside, it turns out this does save the second law of black hole thermodynamics, because as the area contribution shrinks, the entropy of the quantum fields outside grows, because in the process of Hawking evaporation, the quantum fields outside are going from a pure state to a mixed state. So here you have an example where the entropy of fields, of quantum fields, is very deeply connected with the entropy of black holes, but it's not the old dream of completely explaining the area formula. Okay, so now moving to ADS-CFT. Of course, you don't need reminding that entanglement entropy is a crucial role for recent insights on how ADS-CFT works. And we've learned a lot of lessons from the connection between entanglement and geometry. In particular, now we know that the set of states that share geometric dual form a quantum error correcting code. We understand how to reconstruct local operators in the bulk in the entanglement wedge from CFT operators. And the main formula fueling these insights is this formula I'm writing here, which is this FLM formula that generalizes the Ryu-Takayanagi formula to subleading orders in 1/n. So remember that the Ryu-Takayanagi formula tells us what's the entanglement between a region and the boundary and its complement in terms of the area of an extremal surface in the bulk. That's in the case that the bulk is classical, but of course this formula undergoes quantum corrections, 1/n corrections. And these quantum corrections have been argued to take this formula in which we have to add to the area of this surface the entanglement entropy of the fields across it, of the quantum fields across the surface in the bulk. Okay, so the end of my introduction is that it's very important to consider the entropy of quantum fields in the context of gravitational entropy. This tells us about the quantum corrections of this gravitational entropy. And although this formula is very suggestive, and as I have argued, has given lots of insights in black hole evaporation and ADS-CFT, one big problem that we have when we're trying to make sense of this formula is that one field we should always include in this entropy of the fields in the bulk is the graviton. And at the moment, there's no precise understanding for what we mean by the entropy of the graviton. So this formula is the source of a lot of insight, but one of its main parts is still poorly defined. Now, the remainder of the talk is going to be discussing what are the problems behind defining the entropy of the graviton. And from a classical analysis that's going to be looking at the phase space of the graviton in subregions, I'll propose not a completely fleshed out understanding of what you might mean by the entropy of the graviton, but hopefully I'll give some insight for some ingredients to make sense of it.
So Joan, I have like a naive question. I'm not sure actually you're gonna be using it to any extent or whatever, but like you were invoking the second law of thermodynamics, right?
Yes.
And at the same time, you were saying that quantum fields give 1/n or correction to, or G-Newton correction to the, or the zero in G-Newton correction to the Bekenstein-Hawking entropy, right? But
yeah.
Two objects, I mean, although they originate from quantum fields, they are in principle different, right? In the sense that one is like a coarse-grained entropy and the other one is the entanglement entropy between two regions, right?
You mean the gravitational entropy is a coarse-grained entropy and the entropy of the fields is a fine-grained entropy?
Yeah, there's like an entanglement entropy of quantum fields, but like when you talk about like the fields outside the horizon, the entropy that you use in order to plug it into the second law is the coarse-grained entropy, right?
The coarse-grained. What do you mean by coarse-grained entropy?
Well, and like when you involve like the second law of thermodynamics, it's a statistical statement, right?
Yeah, you're right. Yes.
So is there some, I don't know, tension or something interesting to explore there, or like it's completely irrelevant for your talk?
It's completely relevant for my talk, but it's good that you raised this point. I had not stopped to think very much about it. I don't have anything to add. It's an interesting observation. Yeah, I have nothing to say. Yeah. Okay. Yeah, thanks for the comment. Okay, so I'll be discussing what's subtle about the gravitational entanglement entropy, or the thinking about the subspace of gravitational degrees of freedom in a subregion. And that this is subtle is something that is known, and it's something that has been studied in a lot of detail for gauge systems. So the plan of my talk is to first review what's known for gauge systems, and in particular, I'll be focusing on just U1 gauge theory, just the Maxwell field, and then I'll move on to the gravitational case. Okay, so now I'm gonna introduce subregions in gauge theory. And the problem of considering subsystems in gauge theory is that the observables that you have in a gauge system have to be gauge invariant. And that means that some of your observables are intrinsically non-local. Some of your observables or some of your degrees of freedoms are intrinsically non-local. So let's say that we're thinking about electromagnetism. the basic observables would be like the position space type variables, which for electromagnetism are the vector potential and the electric field. The electric field is gauge invariant by itself, but as you know, the vector potential is not, and that means that's not something you can measure. You can measure gauge invariant combinations that you make from it. And of course, the most natural gauge invariant observable that you can make from the vector potential is its holonomy around the loop, which is called the Wilson loop. This is this observable here. But because we need a closed loop to define this observable is intrinsically non-local. So some of the basic observables of gauge theory are intrinsically non-local in this sense. And when I say I'm going to use interchangeably the word observable or degree of freedom. But then if we're thinking about such degree of freedom, and we also want to think about this region here in red, it's hard to decide what to do with it when we're dividing our system into subsystems.
So Joan, like EI is supposed to be electric field, or what?
EI is the electric field, that's right, yes. It's the, which I'm going to use phase-space language afterwards. EI, so the electric field is the canonical conjugate variable to the vector potential. You can think of the electric field as the momentum type of variable for the electromagnetic field, and the position type of variable is the vector potential.
But for, I'm like a stupid question, like maybe I'm not saying something, but for a U1 gauge theory for electromagnetism, we can use F, like this, the field strength, right? And this is gauge invariant, like it's gonna have like magnetic field, electric field, right?
Yeah.
We can repackage like this information in A and then use Wilson loops, right? But if we use like Wilson loops and, okay, I would say that you're saying that like Wilson loop is gonna be some sort of like a magnetic, it's gonna be like a magnetic flux, so like we're using like magnetic flux. And
yeah.
But
yes,
in a non-abelian theory, like EI is not going to be gauge invariant, right?
No, EI by itself is not gauge invariant, but you can consider traces of EI or traces of products of EI, which is going to be gauge invariant.
Okay, so this is the idea. Okay, very good.
Yeah, yeah. So, so the problem with systems with gauge symmetries that we have these extended degrees of freedom, and when we're trying to divide our system into subsystems, it's not clear what to do with these degrees of freedom when they go across the boundary of our subregion. So I want to emphasize that this is a problem that survives. It's a problem that's independent from the first problem in quantum field theory I discussed in this talk. That was the problem of smearing with test functions. This is a problem that survives when you put the theory in the lattice. So it's a problem of gauge of even quantum mechanical systems. It's not a field theoretic problem. It's a problem with gauge symmetry that survives discretization. Okay, so this problem has been cited in a lot of detail, and now we have several definitions for what we might mean for the degrees of freedom inside the subregion. And I'm going to take the definition that Casini-Huerta and Rosabal proposed in a very nice paper, I think 4 years ago. And basically, in their paper, what they advocate for is to think about the observations that you can do inside a region. And so, again, I'm mixing observables and degrees of freedom, but to think intrinsically in terms of the observations you can do inside the subregion. And that amounts to choosing an algebra of observables that you associate to the region that you're thinking about. So to make a quite long story short, their prescription says that thinking about a region for a gauge theory, or defining what you mean by a region in a gauge theory, is equivalent to choosing some boundary conditions for the fields, for the gauge fields. And to give some picture about how that comes about, this is a bit, there's several choices for these boundary conditions, and these several choices are more or less in correspondence to how we're thinking about our system. So we might be thinking about our system in position on a momentum space. And again, remember that for the electric field, the momentum type of variables are the electric fields, and the position type of variables are the Wilson loops. Now, in the prescription of Casini-Huerta and Rosabal, if you're thinking about your system more in this language, in momentum type of variables, it turns out that defining, so the natural definition for a subregion in these variables is a definition that puts some boundary, fixes the electric fields on the edge of this subregion. Or otherwise, there's another option, which is when you're thinking about the system in this position type of variables, in which what you're fixing is basically the gauge potential in the boundary of this subregion. So there's a number of choices that we have, according to these authors, when we're trying to define the subregion of a gauge system. And these options are in correspondence with boundary conditions. So once we've chosen one set of these boundary conditions, what happens is that our state decomposes into superselection sectors, like I'm doing here. So for example, if we've chosen this electric center, so we have defined our subregion in terms of electric fields, I'm going to write my state in terms of an incoherent sum of states at fixed values of the electric field at the boundary. And then once I've written my state in this form, it's straightforward to calculate the entanglement entropy. You just apply the usual formula. And you will find that it decomposes into two parts. There is this part here, which is an average over subsectors. So this P E sub delta is the probability of finding a certain electric field at the boundary of the subregion. So this is a statistical average of the entropies within each of these subsectors. And then to this quantum entropy, you have to add some classical entropy, which is the entropy of this probability distribution, which is the probability of finding our system at a definite value of the electric field at the boundary. Okay, so let me give some comments about this. This is I have condensed a lot of information in this slide. So the most important thing is that there's nothing that is fixed at the boundary. So I just said that we define our subregion in terms of the observables that we assigned to this subregion. And if we choose to think about the subregion in terms of electric fields, then it turns out that it looks like the electric field, we have to choose a boundary condition for the electric field. So what's really happening when we're choosing this boundary condition for the electric field is that the algebra of observables that we're associating to that subregion drops the canonical conjugate to the electric field in the boundary. So we have an algebra for which there are some operators, in this case, the electric fields in the boundary, that do not have any canonical conjugates. That means that this algebra has a center, that there's a set of operators that commute with everyone else in the algebra. And those are precisely the electric fields in the boundary. And they commute with everyone else in the algebra precisely because we dropped their canonical conjugates. That doesn't mean that the electric field is fixed to some specified value at the boundary of the subregion. It just means that that I cannot change the value of the electric field just by acting with elements of my algebra of operators.
Just a stupid question. So what gives us PEs? I mean, like these probability distribution?
Yeah, these are state dependent. So you hand me a state. I look at the state in a subregion, and there will be some probability of the electric field in the boundary to be in some state or some other state. That's a probability I can calculate from the state you gave me. So it's a state dependent probability. And once I have written the state in this form, so this electric field defines a superselection sector because I cannot change it by acting with elements of my algebra, but it could change just through time evolution. So sorry, to answer your question, this probability just depends on the state. Does that satisfy you?
Joan, a related question. So is PE, do you calculate that probability by doing a path integral over the fields in all space, but fixing a boundary condition for the electric field at the boundary of the region?
Well, I have not mentioned any path integral, but I think this might be a way to do it. Yeah, so if you imagine preparing your state, for example, with a path integral, these PEs are just the probability of the electric field to take a certain value in the boundary of the subregion. And if you have a state that's defined through a path integral, you can calculate these probabilities with that path integral. And yeah, that would be a way to calculate them. But more generally, it's just the probability of the electric field to take a certain value in the boundary. It's just something that you can calculate with if somebody hands you a state.
Another question. So if we have a system of global symmetry, so shall we think of? I mean, like in this spirit, like shall we think of like having a row, so like reduced density matrix that is a sum of the superselection sectors, in which these superselection sectors are like different number of charges inside the subregion, and then PEs are like probability distributions of having these different charges, or like how to think of it then?
Well, this electric field is just the configuration of the electric field on the boundary of our subregion. So it does not necessarily correspond to net charge inside.
No, I understand, but I'm just wondering, like, is this structure generalizable in a sense that, like, do you see this structure in other situations? And I thought that maybe if you have like conserved charge, this
Yes, I think this structure generalizes to other systems, but I'm not sure. So something that's important here is that I'm discussing subsystems of gauge theories. I think that if you have, I don't want to make a comment about global symmetries. I'm not sure this is directly relevant.
Yeah. So what's confusing for me is that then, like, I would see. I mean, I don't understand like why we would drop like the. I mean, like, there's like this idea of a center. I'm not sure like there you would have like, the center.
Well, yeah, okay. So that's because you didn't understand that because I didn't explain it. So I apologize for not having done that. So this is all comes back to this construction of Casini-Huerta Rosabal, and basically what they're doing is defining systems through the observables that we associate to these subregions. And one thing that's special for gauge systems is that there are some constraints, some constraint operators that have to be identically satisfied. And for electromagnetism, this is basically the conservation of the electric flux. So that means that by knowing, so the electric, I'm considering a gauge, an electromagnetic system that does not have charges. So the electric field lines cannot end anywhere. They have to continue smoothly, in particular across the edge of a subregion. So that kind of links the inside with the outside of the system, because if I know the electric field at the boundary from the inside point of view, I also know it just outside of the boundary, just by continuity, because the electric field is conserved. Now, the reason why these electric fields are elements of the center is because they are a shared operator between for the inside observers and the outside observers. And when you want to talk about independent subsystems in quantum field theory, you want to talk about sets of operators that commute. Now, if I have an operator that belongs to both the inside and the outside, I have to drop its canonical conjugate. Otherwise, I'm going to be able to change something that can be measured outside only by acting in the inside, or vice versa. So I'm just not giving justice to this, but the reason we have to drop algebras with centers is because the constraints in electromagnetism link the fields inside to the fields outside. And then microcausality, which is an essential ingredient for distinguishing subregions, forces us to drop the canonical conjugate when we're considering an operator that's shared between the inside and the outside of a subregion.
Thanks.
Okay, thanks for the question. So, yeah, so the point is that we're thinking about algebras of operators, and there's nothing that's physically being fixed there. It's just that the operators that we allow ourselves to measure don't allow mixing or jumping between these different superselection sectors. So the choice I've discussed so far is the so-called electric center choice that defines a region by the measurements of the electric fields that we do on that region. But we could have chosen the magnetic fields or the Wilson loops, and then we would have a different definition for what we mean by that subregion. Now, these definitions are actually truly different, as we will see in a second, but their difference is a very subtle and very UV difference that lives really at the edge of this subregion. And if we consider measures of entanglement that are UV finite, for example, mutual information and relative entropy, it turns out, as Casini-Huerta and Rosabal argued, that they are completely independent to how we define the subregion, which algebra we're choosing. So just a cartoon for this picture of superselection sectors I discussed. Somehow the space of states splits into these level sets when we're considering subregions. And within each level set, the electric field in the boundary does not change. And by acting with the operators that we kept in our subregion, we can move within this level set. But then our system may have also support in other level sets that have different values of the electric field in the boundary. And we can move within each of those, but we cannot jump from one to the other with acting with the operators that we associate with the subregion. Okay, so now to illustrate that these choices of algebras that we associate to subregions are truly different, you can compute the entanglement entropy using the formula I showed earlier that had this Shannon term. Sorry to go back. So there's this formula here. So once we have chosen an algebra, we can write our state this way, and we can compute the entropy in this way. And the entropy you compute does depend on which algebra you chose. And here you have two examples of this. So I'm considering the Maxwell field in the vacuum, in flat space, and across a sphere. This is in 4 dimensions. So it turns out that if you do the calculation using the electric center, which is the algebra that I just have been discussing, you get this answer here. There's the area law that we discussed in the beginning of the talk, and then there's a subleading divergence and ... And this subleading divergence has a very particular coefficient, which is related to the central charge of the Maxwell field. These coefficients of logarithmic divergences are usually considered universal because you can more or less, well, not very rigorously, you can argue that they are related to central charges. But it turns out that if you do the calculation using a different definition for what you mean by entanglement entropy, in particular one that's based on the mutual information, what you will find is that you get an area law divergence, but then the coefficient of this logarithm changes. So indeed, the fine-grained properties of the entanglement entropy that we associate to a subregion are very sensitive to how we defined the subregion, and in particular to which algebra we associate to it. So as I said earlier, these subtleties should drop from quantities that have a nice UV limit. For example, mutual information itself, which is what you get if you keep epsilon finite here, or relative entropy. Okay, so now to recap what I said so far about gauge systems. The main subtlety with gauge systems is that they describe extended degrees of freedom that do not naturally factorize across subregions. Then we have to make some decisions when we're talking about subregions. We have to make a choice that's not completely natural about which algebras of observables we associate to these subregions. There are several choices that seem reasonable, but then when you compute the entanglement entropy in either of these choices, you get different answers, including for the terms that are so-called universal. Okay.
So John, so the argument for universality of these terms was just that they are not going to be touched by the rescalings of the U regulator, right?
That's right. So,
but what you just discussed is that there's some discrete set of choices that you make in defining this quantity, right? This has little to do with UV regulation, right? It's something else, and then it's not surprising that you get different results, right? So like this whole argument was not safe proof from the point of view of these additional subtleties.
I agree. Yes, and the argument that relates these numbers to the central charge. So another argument why this coefficient should be robust is because you can argue. So it's an argument that's based on the path integral that directly relates these numbers to central charges. But this argument uses the replica trick and uses the path integral, and that's a formulation in which these subtleties about Hilbert space is quite hidden. So yeah, that's just to add to your comments. If you assume the replica trick and you hand wave a bit about what you do with the tip of the cone that appears when you have the replica trick, then you can argue that, okay, these numbers should be related to central charges and therefore should be intrinsic properties of the theory.
And what's the relevant value of central charge? Sorry for the ignorance.
What's the relevant, sorry?
Value of central charge?
So this is the, I think it's the C central, I may say this wrong now. I'm not sure if it's the C or the A central charge that matters in 4 dimensions.
Okay.
Actually, I think it's the A central charge. So yeah, so in 4 dimensions we have 2 central charges, and I think it's the A coefficient that's controlling this particular divergence of the entanglement entropy across a sphere in the vacuum. And
so
this is
what you're saying is that the central charge is defined by the properties of the stress tensor, or is not going to be sensitive to these subtleties, but the
yes,
property defined in terms of entanglement entropy is going to be sensitive as hell.
That's right. Yes, yes, that's what I'm saying. Thanks. Okay, so this concludes my discussion about gauge systems, but I'm going to come back to them in a second, actually. Now I'd like to move on to gravity and then introduce some techniques, illustrate how these techniques work for electromagnetism, where we are now familiar with what happens, and then explain what these techniques predict for gravity. So just some preliminaries when we're considering the gravitational problem. We've seen that the main subtlety in gauge theories when talking about subregions is that there are some observables that are non-local, so it was not clear how to assign them to the inside or the outside of that subregion. So in gravity, there is a version of this problem, but that problem is much more severe. And the reason is that there's absolutely no local observables in gravity. The reason why there's no local observables in gravity is because all observables in gravity should be diff invariant. And a local observable is an observable that would have support just in one point, but a point is not something that you can discuss in a way that's detached from coordinates. To specify where a point is, you need to introduce some coordinates and then tell me what's the value of the coordinates in which this point sits. So this is a coordinate-dependent definition. If I change coordinates, I will have to change the characterization of this point. That's something that's not acceptable in a diff invariant theory. So in diff invariant theories, there's no local observables.
So somehow, if you want to define a point in holography using some boundary data, you're saying that there's also some hidden subtlety. For example, like in the kinematic space program, like there was the idea of defining a point by looking at some intersections of various Ryu-Takayanagi surfaces and so on and so forth, right? I mean, naively you would say that this is a boundary quantity, so it's like different variant. But maybe the subtlety here is that you have to specify, like what you mean by the boundary, what you mean by the asymptotic boundary.
Yes. Yeah. So I think you can. There is a way in which you can talk about points which is in relation to other points, if these points are fixed. So in ADS-CFT, you can probably talk about points in the bulk by putting them in relation to points in the boundary. So the type of differs we don't consider diffeomorphisms that move the boundary gauge symmetries in ADS-CFT. And if we talk about points in the bulk in relation to other points in the boundary, then I think these are well defined. But then if you think about it, this is not a local observable anymore because it's an observable that lives in 2 points. It connects the point in the boundary and the point in the bulk. So somehow you could think about it as some kind of Wilson line that ends in the boundary.
Okay, so basically you're saying that like something as local as a point in the bulk in holography is actually defined as some very non-local object involving also points or structures on the boundary.
Yes, that's exactly. So, and there's nothing that lives on its own just in one point in the bulk.
Okay, very good, interesting.
So this is the reason why there's no diff invariant observables, local observables in, well, that's it. No diff invariant local observables. This is much worse than for spin 1. So for spin 1, we found the Wilson loops that were not local. but then the electric field did live at a point, and that's something that we could measure locally. So there's no such thing as the electric field in the gravitational case. So what's worse, it seems that generic surfaces that would specify what's our subregion in a diff invariant theory are also not gauge invariant. That's because the general way we would characterize a surface or the edge of a subsystem would also require the introduction of some coordinates and giving the embedding map of that surface in the bulk. So it's not even clear that the notion of a gravitational region is compatible with diff invariance in general. Of course, I will argue that there is a sense in which these things actually do make sense, but a priori it seems quite puzzling. Now, the technique I'm gonna use to discuss subregions in gravity are phase space techniques. So I'm gonna now give a quick overview of the phase space of classical systems. Then I will apply these phase space techniques to the photon and then see what the phase space techniques say for the graviton. So if we're talking about degrees of freedom, it's very natural to talk about phase space because phase space is the space of degrees of freedom of a system. And the main object that lives in phase space is the symplectic form. Let me remind you that the symplectic form is a two form in phase space. So that's an object that you feed it two vectors and it returns you a number. And it does so in an antisymmetric way. If you introduce these two vectors, in the opposite order, it gives you minus the number that was giving you earlier. So this is the main structure that we have in phase space, which is the space of degrees of freedom, as I said. Or more covariantly, you can think of phase space as the space of solutions to the equations of motion. This is actually quite a neat way to think about phase space. We are sometimes told that phase space is a structure that's very incompatible with special relativity because it seems to speak about position and momenta. That's not the case at all because there's one way to think about phase space completely covariantly, which is the space of solutions to the equations of motion. So if you give me a position and a momentum, that's giving me a set of initial data. And if I have initial data, I can solve the equations of motion. So the space of initial data is in correspondence with the space of solutions to the equations of motion. And that's a completely covariant notion. So if I just talk about solutions to the equations of motion, that's clearly completely covariant. So if you have not seen these things before, the symplectic form of a one-dimensional particle is just dq where it's dp. And this is the origin of the funny minus sign that we see in Hamilton's equations and the asymmetry between positions and momentum. Now I'm gonna, of course, the main subject of this talk is systems with gauge symmetries. So let me tell you how you deal with gauge symmetries in phase space. So the common way to think about systems with gauge symmetries is by thinking about a space that's larger than the space of true degrees of freedom. So in the case of electromagnetism, we normally would chart this bigger phase space by the sets of possible three vector potentials and electric fields. That's larger than the true phase space of the system because this space, for example, distinguishes configurations that are related by gauge transformations. Now, the way gauge symmetry comes about in this language is that we are living in this large phase space, and on a particular constraint surface in that phase space, and in the case of electromagnetism, that surface is going to be the surface where Gauss' law is satisfied, so the surface that considers electric fields satisfying this equation. Then in that particular surface, you discover that the symplectic form has null directions. That tells you that there's some degrees of freedom that you're trying to describe in that phase space that are not really degrees of freedom, because symplectic form evaluated on true degrees of freedom cannot vanish. If it seems to have some directions along which it's vanishing, it means that you have some redundancies in your description. And of course, these redundancies here are just configurations that are related by gauge symmetries. Now, if you want to discuss the symplectic structure in the true phase space of gauge inequivalent configurations, what you have to do is to get rid of this direction here, G. You have to get rid of the distinction between configurations that are related by gauge transformations. And this can be done by basically doing Kaluza-Klein type of reduction along these directions. So this is the picture that I'm describing. We have here these arrows denote like the large phase space of all possible A's and E's that include, so distinguish between configurations that you would relate by a gauge transformation. And then on this large phase space, there's a particular constraint surface that I'm plotting here as a cylinder. And on this constraint surface, we discovered that the symplectic form has null directions, which means that there's some non-degrees of freedom there. And these null directions I'm drawing here in red. So if I move along this direction, the symplectic form vanishes. So if I contract the symplectic form with a vector tangent to this direction, it vanishes. The true space of gauge inequivalent degrees of freedom is given by the base of this fiber bundle, which is gamma bar. So the fiber bundle is this constraint surface in which the fiber are the gauge transformations. And the base of this fiber bundle is the space of true gauge inequivalent configurations. And we can get to that space by just doing a Kaluza-Klein reduction on this object, on the symplectic form. And then, of course, a necessary condition for you to be able to do this symplectic reduction is that these directions G that we want to dispense with are symmetries of the symplectic form. So this is just like in Kaluza-Klein reduction, we can reduce over a metric that has a symmetry direction. Okay. Now, I'm insisting on this fact that these gauge directions should be symmetry directions of the symplectic form, even though this is a truism geometrically. So if you look at this formula, you will see that it's always identically true.
Sorry, like this one direction was a circle because it's U1, like that's why you...
Well, this is a cartoon, but indeed, in this case, I think it illustrates this fact that this is U1. Yeah, but this is just meant to, don't take this literally, this is just...
And if you have a non-compact gauge group, can you have also such a Kaluza-Klein reduction, or it gets...
Yes, I think so, yes.
Okay.
So you will have some non-compact directions, which are the gauge transformations along that group, but if these are symmetry directions of your system, you can just reduce over them. This is just like having a system with translational symmetry. You can forget about the direction that's translational invariant and describe things only in the directions that are non-trivial.
Okay. Well, thanks.
Okay, thanks. So indeed, I'm insisting that these are symmetry directions, but this should be true trivially, because if you remember the formula for, so this is just the Lie derivative in phase space of the symplectic form along this gauge transformation on the constraint surface. Now, if you remember the formula for Lie derivatives of forms, this is the Cartan magic formula. You can write this in terms of the exterior derivative operator and the contraction of the form with the vector that generates the gauge transformation. And then we get these two contributions. This second contribution here should always be identically zero because the symplectic form is closed. Its exterior derivative is zero. And then on the constraint surface, this should always be zero, because remember that on the constraint surface, we have these null directions of the symplectic form. So this contraction of the symplectic form with the gauge direction should identically vanish. So this should always be zero, but sometimes you will find that it's not obvious that it's zero. And that's because it's somehow geometrically not obvious to decide which directions are tangent and which directions are transverse to this constraint surface. So ensuring that this is satisfied helps us do the geometric process of discarding directions that are transverse to the constraint surface when we are constraining ourselves to it. So this is quite a technical comment, but it's going to appear later in the case of GR, and this is why I'm insisting a little bit on it. So just to summarize what I said so far about symplectic forms. So the way we diagnose gauge symmetry in phase space is because it's a non-degree of freedom, and that means it's a null direction of the symplectic form. The way we discard these gauge degrees of freedom is by doing a Kaluza-Klein reduction of the symplectic form along these directions. Now, the main point of my talk, the main physical ingredient of what I'm going to do in the next 10 minutes is that when we are thinking about separating our system into subsystems, for example, to discuss the entanglement between the different parts of the system, this separation of the system into subsystems is a completely imaginary separation. In particular, that means that it does not introduce degrees of freedom to the phase space, and whatever was a gauge symmetry that we could dispense with before we divided our system into subsystems should still be a symmetry that we can dispense with, even when we have considered this imaginary separation. This is very much unlike usual considerations of systems with gauge systems with boundaries. So one subtlety that happens when you have boundaries in gauge systems is that boundaries tend to make the gauge transformations into physical transformations. That's because as soon as you have a boundary, what you were considering before that was a gauge transformation becomes a large gauge transformation, which has more the status of a global symmetry rather than a local symmetry. So that's indeed a feature of gauge systems with physical boundaries. But what I'm discussing here today is not systems with physical boundaries, but systems with imagined boundaries. And these are the boundaries that we imagine when we want to divide in our minds a physical system into subsystems. And a crucial difference with these imaginary boundaries is that they can't introduce degrees of freedom because they are just imaginary boundaries. And if they introduce degrees of freedom, these boundaries would be made of something, which would be these degrees of freedom that we are introducing. So the main thing I'm going to demand in what follows is that what was a gauge degree of freedom continues to be a gauge degree of freedom in the presence of this boundary. And in particular, that means that it continues to annihilate the symplectic form, and it continues to be a symmetry of the symplectic form. So let's see how this works for the photon. So this is quite of a crucial point. If you have any questions, it might be a good moment, or I can take them later.
No, I had precisely the question how it works for electromagnetism. So.
Okay, excellent. So here you have the symplectic form of the photon. It depends on two variations because it's a two-form. And this is how it looks like, which is the variation of the vector potential contracted with the variation of the electric field, and then anti-symmetrizing the two variations. So now let's consider a gauge transformation, which only changes the vector potential but does not change the electric field. This is how it looks like. Epsilon here is the generator of this gauge transformation. And let's substitute that into this formula. What we find is that one of these terms drops because it only varies the electric field in that term. And the variation of the electric field under a gauge transformation is 0. And there's one term that survives. And the term that survives, you can integrate by parts, and it gives you a boundary contribution. And that boundary contribution is, well, the integral along the boundary of the generator of your gauge transformation times the variation of your normal component of the electric field. Now, if this is one of these imaginary divisions that we're considering, this quantity here should vanish because the introduction of this boundary should not introduce any degrees of freedom to our system. And there's two natural ways in which this integral here can vanish. One is to set this generator of the gauge transformation to 0 in the boundary. And the other one is to set the variation of the electric field, normal component to the electric field, to 0 in the boundary. Now this should ring a bell because these are precisely the two boundary conditions I discussed in the beginning of the talk when I was talking about the Casini-Huerta and Rosabal program for algebras of subregions. So there's two natural choices in that program. If you remember, one is to fix the magnetic field in the boundary. That naturally fixes the generator of gauge transformations in the boundary. And then the other choice that I spent some more time discussing was fixing the electric field in the boundary, which came out naturally from this analysis. So indeed, this symplectic analysis is in correspondence with the analysis of algebras of operators in the quantum system. Now, as a final comment about electromagnetism, note that these gauge transformations are always symmetries of the electric form. Sorry, they are always symmetries of the symplectic form, just because you can write this expression here as the total variation of something. And that something is the generator of this gauge transformation, and it's just this operator. So this Hamiltonian here is the operator in phase space whose variation generates the gauge transformation we're discussing. And having such a generator automatically implies that this is a symmetry direction of the symplectic form. Okay, now moving on to gravity. So I'm going to do exactly the same thing I've done for the photon. I'm going to consider the evaluation of the symplectic form on a diffeomorphism. And the diffeomorphism here is just denoted by its action on the metric. So this diffeomorphism is just the Lie derivative of the metric with respect to some vector field. And then, of course, the symplectic form has still one free argument, which is the other vector of phase space that you can feed it. The symplectic form is a 2 vector, and we just substitute one of the arguments. Now, using standard formulas from Wald formalism, you can rewrite this thing in terms of familiar objects in phase space. So notice that this is an integral over the boundary of the subregion we're going to be considering. And that's a good thing, because if our subregion didn't have any boundary, of course, this diffeomorphism should automatically be a gauge symmetry. So it should automatically annihilate the symplectic form. And indeed, it will be the case when the boundary is empty. But if there's a boundary, we have boundary subtleties, just like for the photon. And there's two participants to this subtlety. One of them is the variation of the nether charge with the nether charge of that diffeomorphism we're considering. And the other one is the term that appears when you consider the variational principle in the action, the boundary term that you get when you have to iterate by parts the variation of the action. So there's known formulas for this, and we can just evaluate this in GR. So I'm going to do this evaluation in what follows, but first I need to introduce some notation. So this is the kind of division I have in mind. We have some space-time, there's some boundary that we're considering, and we're going to be writing everything around this boundary. So it's natural to take coordinates adapted to the boundary, and this is what I'm doing here. So I'm taking these yi coordinates that span the boundary, and then I'm taking normal coordinates in directions transverse to the boundary, and there's two of them, one that moves us in the Cauchy slice in which this boundary lives, and the other one that moves us in time. So that's why we have xa here, but these 8x2 values, 0 and 1, 1 is the spatial direction, 0 is the time direction. And then in the other coordinates, we have two leading order in the distance to the boundary. We have just the induced metric on the boundary. And then to first order, we have the extrinsic curvature. Now, it will be convenient to divide the intrinsic metric and the extrinsic curvature in terms of its irreducible parts. And that means I'm going to write the induced metric in terms of its determinant and its determinant want piece. So this is basically the area form. This omega here is basically the exponential of the area form, sorry, the logarithm of the area form in the boundary metric. And likewise, for the extrinsic curvature, you can separate between the trace and the traceless part in the directions tangent to the boundary. So this k bar here is the traceless part of the extrinsic curvature. Now, if you just evaluate this expression I showed earlier in these explicit choices, you find that there's 3 types of diffeomorphisms that participate in this analysis. So I'm going to need like 5 more minutes. Is that okay?
Yeah, that's all right.
Thank you. So there's 3 types of diffeomorphisms that appear in this analysis. The first type are boundary diffeomorphisms, which are diffeomorphisms that are tangent to the boundary of our subregion. The other types of diffeomorphisms are boosts, which fix the edge of the subregion, and translations, which would move the subregion. Now, for each of these diffeomorphisms, you find the following. For boundary diffeomorphisms, you find that they are always symmetries of the symplectic form, and they are null directions of the symplectic form if we fix the conformal structure of the induced metric on the boundary. For boosts, you find that they are also always symmetry directions of the symplectic form, and they are null directions of the symplectic form if we fix the area density of the boundary. And this is just the usual statement that the area is the generator of boosts in general relativity. And then the ones that are more interesting are the translations, the translation diffeomorphisms, which are diffeomorphisms that would move the boundary of our subregion from its current location. And then for this, it's more subtle to decide whether they are Hamiltonian, whether they are symmetries of the symplectic form, and whether they are null. And remember that our physical condition is that the symmetries that have support on the boundary should still be, sorry, the differs that have support on the boundary should still be symmetries of the symplectic form and should still annihilate the symplectic form. So what we're going to demand now is that this is also true for translations. So this is the expression that we get when we evaluate this expression. And the objects that appear here have all been defined in the previous slide, although there's a lot to digest here. So here you find, for example, Ka. This is the trace of the extrinsic curvature. Epsilon h is the volume form on the directions tangent to the surface. And epsilon ab is the binormal on the normal plane to this surface. And then this zeta b is this translation vector normal to the surface. So we get an expression of this type that I'm now going to analyze. There's two lines to this expression, and basically the take-home message is that the first line is an abstraction to this diffeomorphism being a null direction to the symplectic form. And the second line is an abstraction to this diffeomorphism being a symmetry direction of the symplectic form. This connects to the subtlety I was discussing in the beginning of my talk about symmetries of the symplectic form and null directions to the symplectic form. Now the goal is to demand that these two lines vanish independently, and this can be achieved by the following boundary conditions. These are boundary conditions that fix the trace of the extrinsic curvature to be 0, and that fix the changes in the conformal class of the induced metric to have 0 inner product with the traceless part of the extrinsic curvature. So what that means is that the same analysis that we did for electromagnetism translates to gravity if and only if we're considering surfaces that have 0 trace of extrinsic curvature and variations that preserve this minimality of this entangling surface. And we can consider different sectors that are labeled by the conformal class of the induced metric subject to this condition. Now, you might be worried that I'm now claiming that the only subregions that make sense in GR are subregions that are bounded by minimal surfaces. But if you remember my motivating examples in this talk, which were bifurcation surfaces of horizons and Ryu-Takayanagi surfaces, these are indeed surfaces of this class. So the interpretation is indeed that the state of a gravitational subsystem composes into superselection sectors. In all of these superselection sectors, the extrinsic curvature is traceless, and these superselection sectors are labeled by the conformal class of the induced metric, subject to this condition. Now, I'm running out of time, and I have a couple slides. Well, I have run out of time already, but I have a couple slides explaining the interpretation of this condition. Basically, what this condition does is to discard local deformations of the surface that would move us to nearby extremal surfaces in the same background geometry. So this condition here is there to guarantee that we're considering only one entangling surface per spacetime. So I'm gonna just skip this interpretation because I'm running out of time, but I'm happy to elaborate on it if there's questions. And I'll just recap what I said about the graviton. We have a principle which is that subregions are imaginary separations, and that means that they don't introduce degrees of freedom to the phase space of our system. Physically, that means that we want to be able to still symplectically reduce even in the presence of these imaginary boundaries, and that imposes some non-trivial conditions on the variations of the fields on this edge of the boundary. In particular, for GR, we find that the boundaries have to be extremal surfaces, and superselection sectors are labeled by the conformal class of the induced metric subject to this constraint. So for the future, I would like to understand this local deformability claim that I have not explained in ADS-CFT. This is only an infinitesimal claim. I do not claim there's any finite deformations available for Ryu-Takayanagi surfaces, but I claim that to first ordering deformations, you can find solutions. And more ambitiously, I would like to understand better quantum corrections to black hole entropy in the language of the entanglement entropy of the graviton. In particular, there's this famous mismatch between a calculation that sent it for the quantum corrections to the Schwarzschild black hole and the prediction from loop quantum gravity. So SEN finds this coefficient for the logarithmic divergence, for the logarithmic correction to the entropy of the black hole, and loop quantum gravity seems to output something with a much simpler coefficient. I would like to understand whether there's any wiggle room in terms of algebras of observables in this calculation, and more generally, I would like to understand the technology that's already available for quantum corrections to black hole entropy in terms of Hilbert space of the graviton and the entanglement of the graviton. Thank you.
Any more questions? Is there any?
I have a question about precisely this last slide. So I might have asked you this already, but in any case, so these are calculations for asymptotically flat black holes, right? But you can do a similar calculation for asymptotically ADS black holes.
Yeah.
Right? And in all cases, I think that what you get is that, so if we look at the pure gravity sector, then corrections in G are the same as corrections in H bar, because they both come in the same place in the path integral.
Yes.
So, but in both cases, the one loop corrections, which are the corrections in H bar, take the same form as in your slide. They're log of A over 4G with some prefactor.
Yeah.
But so could you explain how is this related to the FLM calculation? Because in the FLM story, I would expect to get a correction that is of order G to the 0 and not log of G.
Yeah, I remember you asked me this before.
Could you remind me the answer then?
I'm not sure I had a convincing answer. I guess we should revise where this intuition comes from, that FLM predicts that the correction is going to be order G. So, yeah.
Let's put it. Let me put it another way. The corrections that you're showing here, would you interpret them as FLM terms?
Yes.
Okay.
Yes, I think these are FLM terms. Yes.
Okay.
It's just that this is the next power in 1 over G.
Mm.
And it's okay, it's not a power, it's a logarithm, but sometimes powers become logarithms. But in an expansion in 1 over G, this is kind of subleading compared to the leading term.
Right.
Sorry, it's an expansion in G, not in 1 over G. Expansion in G, this is subleading. It's not a power, it's a logarithm. I don't have a better way to answer this. But I think these are FLM corrections.
So John, for electromagnetism, you had a choice, right? I mean, you could pick like either E, right?
Yes.
Like for certain sectors, or I guess I, right? So for gravity, do you have to get such a choice, or I mean,
well, that's my question. I don't know what's the answer to this. The way these numbers are reproduced are by looking at the Euclidean path integral of GR. So if you want, it's a very replicative kind of approach to understanding the entropy. In that approach, you're kind of missing the subtleties about the observables and the Hilbert space that you associate to a subregion. The Euclidean path integral just does not speak in the language of the Hilbert space, and these subtleties are missed. So one thing people say is that when you're doing the Euclidean calculation, you implicitly have in mind a choice for all these subtleties that appear when you think in terms of Hilbert space. So I'd like to understand whether that's the case also in gravity, and whether there's other choices that would be acceptable from a real-time point of view, from a Hilbert space point of view, and whether these choices would change this number.
And what I find interesting in what you discussed, like about gravity, is that, I mean, there's been these ideas about, defining holographic screen where you wish and so on and so forth. But like what you seem to be saying is that at least one choice that you can consider for to deal with the gauge symmetry of gauge principle for gravity is just to focus on extremal surfaces, right? And that rules out like an arbitrary choice of a holographic screen if you want to discuss entanglement for graviton on the left, say on the left, to the left with to the right.
Yes, yes, indeed. That's I have to say. So not everyone agrees. Other people that have thought about this problem disagree with this conclusion. I should disclose this, but this is my interpretation of the calculations I presented, and I stand by this interpretation.
And the last comment, maybe it's not even, it's a comment, it's not a question, is if you calculate the entropy of a black hole, right? Like you can think of it as a term, like entanglement entropy for the term of the double state, right? But somehow like this discussion seems to be pointing out in a direction that if you want to calculate the thermodynamic entropy of gauge theory, then you like, I mean, there seems to be some subtlety, right? In a sense that you know, like you consider a gauge theory, you consider a term of a double state in double copy, right? And then it is like gravitationally when you calculate the, you know, like the entanglement entropy between left and right side for holographic theories, you seem to run into these problems at the subleading order in Newton, right? That there are many answers.
Yeah.
With possibly many ways to define entanglement entropy, right? But on the other hand, it is like superficially you just think of like the thermal entropy in gauge theory. So is this object well defined, or you have like some subtleties there as well?
That's interesting. I haven't thought about this.
And people do calculate on the lattice, right? And like the thermodynamics of QCD is something that I mean.
Yeah, I would expect that.
So maybe it's about purifications. Maybe like the purifications within gauge theories have some subtle features, right?
Maybe there's more than one way to purify.
Yeah.
And to assign like a thermofield double state. Yeah, it's I don't. That's an interesting thought. I always have in the back of my mind the Ryu-Takayanagi kind of construction and subregions in gauge theory, but
sure,
the example you raise is quite interesting. I'll think about it.
Well, it also applies to holography through you know, eternal black holes, right?
Yeah, indeed. So. Yeah, the thermal entropy is a particular case of entanglement entropy for the thermofield double.
Yeah.
So yeah, you raise a very interesting point. Yeah, indeed.
Okay, well, if there's no other questions, let's thank the speaker again.
Thanks, John.